Good evening, everyone. What a treat to see so many friendly faces, a lot of new faces, but also a lot of friendly, familiar faces. If you're not coming from Harvey Mudd College, welcome. It's such a treat to have you here as well. My name is Mike Orson, and on behalf of the Department of Mathematics at Harvey Mudd College, it is a pleasure to welcome you to the 23rd Michael Moody Mathematics Lecture. This lecture series honors the legacy of Mike Moody, who was a cherished friend, mentor, and inspiration to our department. Mike was raised in an old Kentucky family with limited means. His parents valued education, but he knew that if he wanted to attend college, he would have to find his own way to get there and to pay for it by himself. And he did. He received his BA from the University of California, San Diego in 1975 with a double major in mathematics and chemical physics and a double minor in history and philosophy. Pursuing an interest in biological systems, he then earned his doctorate at the University of Chicago in 1979, writing an applied mathematics thesis in population genetics. Mike's first academic appointment was at Washington State University. In 1993, he was invited to spend a year at Harvey Mudd College, and within a few weeks, he knew that he loved our small but ambitious school. Mike joined the college permanently in 1994 and became HMC's first Diana and Kenneth Johnson professor in 1996. The same year, he was named chair of the mathematics department. During his time as chair from 1996 to 2002, Mike helped transform the department by hiring 8 new professors and expanding the faculty to 12. He sought people who would inspire students in the classroom and who had a passion for their mathematical work. At the time of his passing in January 2010, Mike was vice president for academic affairs and founding dean of faculty at Olin College in Massachusetts. That spring, the HMC Alumni Association recognized Mike as an honorary alumnus in honor of his many contributions to the college. The Moody Lecture Series was created by the Department of Mathematics to celebrate Mike's legacy and his love for talks that reveal the joy, mystery, and relevance of mathematics. The series continues through the generosity of his family, friends, colleagues, and former students. And on behalf of Mike's family, I'd like to thank the entire math department and the HMC development team for their unwavering commitment and support of the series. And now, to introduce tonight's speaker, please welcome my colleague, Professor Andres Vindes-Melendez.
I'm going to stand behind the podiums because, it makes me feel comfortable when I hold something. Welcome, everybody. Welcome, Prof. Andres. Yeah, thank you. I see some of my students, so you better respond. It is my absolute pleasure to welcome you to this year's Moody Lecture. Our Moody Lecture is a dear friend of mine who I've known now since, I guess almost 15 years. And I'll tell you a little bit more about him in just a second, but Federico Ardila runs a Instagram page where he puts his names misspelled. So I intentionally put up the misspelled one version of his name right here because I thought it would be a nice addition so that Harvey Mudd holds a place on his Instagram. So let me share some pictures because I love pictures, okay? Well, first of all, I'll maybe mention some of his academic trajectory. So Federico, first, before the academic stuff, is that he's from Colombia, and where he lived till, I think, 17, and then moved to the United States to go and attend MIT for his undergraduate work in mathematics. After that, because apparently he loved MIT so much, he stayed there and received his PhD in mathematics, working under Richard Stanley, one of the fathers of modern combinatorics. Federico has a long list of awards and accolades. I'll maybe point out that he actually has awards for all three areas that in the academic profession we value: research, teaching, and service. And so as a researcher, he's been an invited speaker to the International Congress of Mathematicians, one of the biggest honors that we can bestow on a mathematician in the world. He was awarded an NSF Career Award when he was starting off as a professor at San Francisco State. For teaching, he's been awarded a national MA HIMO Award that represents excellent teaching. And in service, he has, on behalf of the Mathematical Sciences Research Institute, underrepresented program, so MSRI UP, which is a research program now at SL Math up in the Bay Area, has been awarded an award from the MA for excellent programs, of which we have also been awarded as the math department here. I met Federico that's me, if you can't tell, that cute gordito up there, in that middle picture. That was 2011 at a SACNAS conference, Society for Advancements of Chicano, Latinos, and Native Americans in Science, or now it's called the National Diversity in STEM, the NDI STEM conference. And I did not know what I was doing there, but it was in San Jose, so it was close enough to drive from the Bay Area when I was an undergrad at Berkeley. And I met this, really tall Colombian guy, and he's like, "Oh, he's a mathematician, you should talk to him." I was like, "Okay." And then I was like, "Okay, Prof. Ardila." And he's like, "No, none of that. It's Federico." And it's been Federico ever since, breaking down power dynamics. And I think that also depicts his approach to doing mathematics. After 2011, I stayed in touch with Federico, and actually in 2012, he went to do a sabbatical at UC Berkeley, right across the bay, so from San Francisco State, where he's now a professor. And I invited him to come give talks to some summer students that I was working with. And in that picture, it's not only me, which you can hopefully guess which one's me, and also my sister's there. So my sister, my younger sister, was fortunate to also have been taught by Federico. But this is just to share a little bit about the meaning and the impact that Federico has on my academic trajectory. So very early on, I don't think I would have been here in front of you introducing him if I had not had that opportunity. In 2014, I was an undergraduate senior at Berkeley, and I went to a concert. And at this concert, there was a DJ collective, La Pelanga, and to my surprise, Federico was the DJ. Him and his wife and some friends were the DJ. And of course, Prof. Andres had some nice drinks and danced a lot. And Federico goes, "Andres, you're gonna take my algebraic combinatorics class." And of course I said, "Yeah," because that's what you're gonna say at a concert. And the concert ended, and 2 days later I got an email. And Federico said, "This is how you cross-enroll from UC Berkeley to San Francisco State so you can take my graduate algebraic combinatorics class." And it was the first time a professor singled me out in a positive way like that, saying like, I believe that you have the ability to do this graduate coursework. And so I cross-enrolled my fall of my last year at UC Berkeley to take his graduate algebraic combinatorics class. Since then, I fell in love with discrete mathematics and combinatorics because if you know me, I was not a fan of discrete mathematics and in fact, had to take it 3 times as an undergrad. And so that's the picture over there from that algebraic combinatorics class. And it was then that some of those have become my lifelong friends, including Federico. It's so impactful that my family considers Federico family. And in fact, they say, "How's Federico doing?" before they ask me how I'm doing. And so they really appreciate him. And so this is again, how can we do math in community? And Federico exemplifies this. This was when we proved our last theorem for my very first paper. And so that's my collaboration. So Anna Schindler, Federico, and I wrote my first mathematics paper together. And this, as you can see, was like, I think, Google Hangouts. Mathematicians were doing virtual collaborations way before Zoom was a popular thing, okay? And so I truly believe that I would not be where I am if I had not had the support of Federico. Sometimes I think, and like I wrote in my PhD acknowledgements, I would, he believed in me sometimes more than I believed in myself at certain times. And so I am very pleased and happy to be able to introduce my dear friend and mentor, Federico Ardila, as this year's Moody lecturer. So let's give him a warm welcome to Harvey Mud.
Right, can you hear me? Okay. I mean, at this point, I should just give up, right? Like, but how do you, how do you follow that up? Thank you so much for such a wonderful introduction, Andres. I wish you all to have students like Andres and so many of our students that we have that really teach us how to do this job, which we don't really know how to do, and very often they are the ones that kind of lead the way for us to be like, okay, like what they're seeing, I should pay attention to. And it's always been this way with Andres, and so it's really like a wonderful full circle opportunity to come and see him, but also see you all, because I have so many friends in this department that I was realizing I feel really shocked that I had never visited you all. I feel like a bad friend from having so many friends here, but it's wonderful to be here. So thank you so much for inviting me. Today I would like to tell you a little bit about what my friends and I were up to last year. So I got to spend the last year at the Institute for Advanced Study in Princeton. And I got to spend a lot of time doing math with friends. Keep going. So one thing that happened while we were there is that with my friends Sergio Cristancho, Graham Denham, Chris Ear, Jun Ha, and Botong Wang, we discovered some new inequalities for trees and matroids. You talked about mathematics being joyful, impactful, maybe, and relevant, and surprisingly exciting. This has been a project that has been very joyful to me, very exciting, very surprising. I have learned a lot. It's also been strangely relevant to some things that I don't really understand yet. So I want to tell you a little bit about some math that I'm excited about that is very fresh on my mind. This stuff is not published, actually. We're working on the paper right now, but I think it's a nice story. At least I find it interesting. So let me tell you a little bit about my plan. So I want to begin by telling you about some work of Graham and Pollack on distance matrices, and a new result that we discovered about these kinds of distance matrices. And so that'll be the inequalities on trees. Okay. And then I want to tell you about two conjectures about matroids, and how we were able to resolve those conjectures using this theory of Lorentzian polynomials. Now I want to say up front, I actually had never used Lorentzian polynomials before, and like you've never heard of them, I also didn't really know how to use them. So I'm not assuming that you know anything about that. I'm not assuming that you know anything about matroids. I'm trying to give it a lecture that is as accessible as possible. Feel free to ask any questions. I think you probably realize this, but the way that these talks go, it's not meant for you to understand every word that I say, but I really have the intention that you at least understand the vibes of what it is that we're doing here, okay? So let me begin by telling you about Graham and Pollack. I come from a family of storytellers, and I always learned that a good story, you can't start at the beginning. And so actually this is so in some sense that the Graham and Pollack part is a very early part of the story, but it's also a very, like one of the latest things that we found out. Graham and Pollack were mathematicians who worked for Bell Labs in the early 70s. Bell Labs was, and here I'm a little bit outside of my league of knowledge, but Bell Labs was that they were in charge of the telephone company, and they had a monopoly on the whole US telephone system. So it was their job to connect everybody in this country telephonically. And they hired these mathematicians, Graham and Pollack, to think about the mathematics of how do you lay out a phone system that works. Raise your hand if you have ever dialed a phone like by going like this. So it used to be that you would dial these rotary phones and point being that when I would try to call, not Andres, because I don't think you've ever used that, but maybe Dagan, I understood that I would dial the phone and there would be this lag time. Like I would dial and then there's some waiting time. And then eventually it was the phone would start ringing and then Dagan would call. But there was a period that it took to connect. And in this paper from 1971, which is actually, it's a little hard to read for me because it's an internal report of Bell Labs. And so they say like, okay, well, we all know how the Bell system works. And I don't, so it's hard for me to know exactly how everything works. But their goal is that they're talking about this new thing called computers, and how all of a sudden computers are going to enter this telephone system. Computers don't have the patience that you can make them wait like that. They're really trying to find for a much faster system because the telephone company is just the system is becoming too slow. Okay, and so the beginning of the story is telling you what was their proposal for how to come up with a more efficient way of assigning phone numbers. And this is like truth. I mean, this has happened. So what they did is this. So I drew a graph there. When I say graph, I just mean there's nodes and there's edges. Okay, and I don't know if this is exactly accurate, but I think it's approximately accurate that each node you should think of as a telephone, and then each edge is a connection, a direct connection between telephones. So you could make like a direct connection from phone number C to phone number E. Okay. But of course, that's a very tiny network, but you should really be having in mind the whole US, a very huge network. And so they are trying to figure out how to assign phone numbers. Now, those of us who dialed rotary phones know that when we were trying to call our neighbor and invite them out to play football with us, I remember my phone number was 2166104, and my neighbor was 2166112. Neighbors used to have pretty adjacent phone numbers. And you kind of want that if you're trying to find some algorithm to connect things. And so what they're trying to do is figure out how do we assign addresses to the nodes, okay? In such a way that the addresses can tell the distance in some way. Okay? And so they say, okay, let's try to, computer scientists only know the numbers 0 and 1, right? So they wanted to, computers talk in zeros and ones, and so they wanted to assign phone numbers that were zeros and ones. So they said, okay, can we assign at each node a string of zeros and ones? And then the idea is that if two phone numbers are one edge away, then their phone numbers should only change in one digit. This is what's called the Hamming distance, is how many changes you have to make to the phone number. Okay? And so then they said, okay, let's try that. So let's make a distance matrix. So here's the graph. And what I have here is a matrix where, for example, this 3 means that between A and D, the distance is 3. The shortest path from A to D takes 3 steps. And so please double check your favorite entry here, that this 2 means that from B to C, you should be able to get there in length 2. So that's the distance matrix. And now they're looking for addresses that have those distances. So you want that the address of A and the address of D should be different in 3 positions because the distance is 3. Now, they quickly realized that this cannot be done. And this cannot be done because zeros and ones form a cube. And cubes don't have triangles. And ACE is supposed to be an equilateral triangle, and cubes don't have equilateral triangles. So then they said, okay, what should we do? Let's assign a joker star that can be a 0 or a 1. So now each address is going to have zeros, ones, and stars. Okay? And you want that the distance in the network should be equal to the Hamming distance of the addresses, meaning the number of positions where one position changed from a 0 to a 1. And stars are considered like jokers that can morph into zeros and ones. Okay, so here's like the distance between 0 and 1 is 1, but star actually can be 0 or 1. Okay? And that's what they were trying to do. How do you do that? And of course, you want phone numbers to be short. So then their question was, how do you find the minimal possible length of the addresses for this to be possible? That's what they were interested in. So does anybody have any questions about what we're trying to do here? See a couple of friends that I hadn't said hello to. Okay. So get this, and this is where the story gets really weird. Matrices have eigenvalues. Why would you compute the eigenvalues of this matrix? That seems like a really strange thing to do. No? Doesn't it seem strange to you? Like, why would you care about the eigenvalues of this matrix? What they realized is that the eigenvalues of this matrix were the key to this problem. So here's something that they proved. They proved that the shortest address, the shortest length of the addresses that you can give is greater than or equal to the number of positive eigenvalues of this matrix and is greater than or equal to the number of negative eigenvalues of this matrix. So if you want to know how short your addresses can be, you actually need linear algebra. You don't have a choice. You need to go like either do it by hand if you know how to do it, or ask your favorite software, what are the eigenvalues of this matrix? Now, one thing I want to say, I took linear algebra. The longer you're a mathematician, the longer you realize you don't know linear algebra. You never stop learning linear algebra. So, okay, here's a linear algebra thing that I think many of you know, but probably many of you have forgotten. When a matrix is symmetric, the eigenvalues are real. I actually had forgotten that. If a matrix is symmetric, if the ij entry equals the ji entry, then the eigenvalues are real numbers. And there's some weird real numbers that are very hard to compute, but you can approximate them, and then you just have to know what are the positive and negative roots, and that's what you do. I'm going to sketch a proof because I think it's very beautiful. But before I sketch the proof, I want to make it very clear, you're not supposed to understand this proof while I say it right now. But you're supposed to get the vibes. Okay, suppose that you're able to give addresses, and now you're gonna, so this is a trick in linear algebra, that a matrix is the same thing as a quadratic form. So you're gonna take the distance between u and v and multiply it by u times xv. Those are variables. And so you're gonna get this long polynomial in many variables. Okay? It turns out that this is equal to the sum from I equals 1 to the length of the addresses of the sum of the x's where the ith coordinate is 0 and the sum of the x's where the I coordinate is 1. Because you get a distance whenever you have a 0 and a 1 in the address. Okay? Now you're going to say, okay, whenever I have a times b, this is a and this is b, that's the same thing as a plus b squared minus a minus b squared divided by 4. Just a simple kind of algebra trick. And that means that this thing is a sum of ng squares minus a sum of ng squares, where ng is the number of the addresses. Okay. Now here's a linear algebra theorem that I didn't know. If you're able to write the quadratic form as a sum of squares minus a sum of squares in this way, then the number of terms here has to be at least the number of positive eigenvalues, and the number of terms here has to be at least the number of negative eigenvalues. This is called the Sylvester's law of inertia. Okay. End of proof. Okay. So, like I said, if you got it great, I don't think I would have understood it right away, but I think you can just see what the kind of idea is. It's short, it's very clever, and if you know this book called Proofs from the Book, maybe I'll tell the story in case not everybody knows. So there's a book called Proofs from the Book, and it goes by this theory that there's a book in heaven that has the perfect proof for every theorem, and we wish that we had access to that book. And there's a book called Proofs from the Book that are just proofs that are so beautiful that they must be in God's book. And this is one of the proofs in that book. In particular, actually, no, so this is the first part of the proof. The second part of the proof is that then they say, here's their theorem. If your graph is a tree, like this, so it has no cycles, then they found that the optimal size of the addresses is exactly the number of vertices minus 1. And the way that they said it is to say, okay, well, if these things are going to be equal, I need to prove two inequalities. First, I need to prove that it's possible to do it with v minus 1 length. And they did it. They found some algorithm, and if I gave you enough time, you would be able to find an algorithm to do it, because imagine if you only have v addresses that you have to give, and you have v minus 1 coordinates, that's a lot of freedom, right? Like if you have 10 addresses and you get to put 9 coordinates, that's freedom. And y'all are Harvey Mudd students. If I gave you an afternoon, you would know how to do it, even if you were not Harvey Mudd students. But the question is, why can you not do less than that? And what they showed is that it's because this matrix has n minus 1 negative eigenvalues. And they proved that the eigenvalues of this matrix, one of them is positive and the other ones are negative. And they have this very short proof that maybe I won't talk about, and if you want, I can tell you later. But this is the proof from the book, basically saying, like, if you want the shortest possible addresses, then this is the best that you can do, and the reason is linear algebra. And one thing that I find very interesting is that the problem that we started with had no linear algebra, but this is the only known proof. Nobody knows how to prove this theorem using only combinatorics. And okay, maybe there are some people, I know there's some physics majors here who could tell you better than me why this is Lorentzian. This is from physics, matrices that have one positive eigenvalue and the rest are negative, and this has to do with how in a Euclidean product, dot product, the dot product is x1, y1 plus x2, y2 plus x, and as I understand it in Lorentzian products, the time variable gets a minus sign. So, and then they flip the signs. But so this is the earliest appearance that I know of the word Lorentzian in combinatorics, let's say. And I told you this is not the beginning, because actually we only understood, at least I only understood later what our work had to do with this. Okay. Mm-hmm. Oh yeah, thank you. $100 conjecture. Prove that for any graph that has v vertices, the addresses can have length v minus 1. Okay, I told you that for trees, you would be able to do it in an afternoon. If you're able to do it for any graph, you can get your PhD with that theorem. You're probably going to get a tenure track job the next day, because I don't know if you know about Graham and Lovász and their conjectures, but like they would put money on their conjectures. And these are problems that they could not do, and they're some of the sharpest mathematicians in these fields. And they have some dollar conjectures and $5 conjectures, and those are very hard, and I've never solved any of them. When it gets to something like $100 conjecture, that is like, okay, we believe this is a really hard problem, and if you can do it, you're going to need some really new idea. So please try, you know, these things can be solved. And they have some conjectures up to like $10,000 conjectures, which I think Terry Tao managed to solve a $10,000 conjecture. But anyway, this is a very explicit conjecture that nobody knows how to do. Okay, so let me tell you our new result on tree distance matrices. We're going to consider the same matrix, but a little bit different. We're going to start with a tree, but now the tree has length. So every edge has a length. Some of them are longer, some of them are shorter. And I'm going to, again, for every two vertices, look at the distance between them. But actually, I'm only going to do it for the leaves. And a leaf of a tree is like one of these dangling nodes that's not connected to everything. So I drew them in blue. So I'm not going to record all the distances. I'm only going to record the distances between the blue nodes, which are the leaves. That I call the leaf distance matrix. Although I explain here, I want to spend a second looking at this, leaf distance matrices are the same as distance matrices, but we only care about the leaves. And it's, if you review the appropriate linear algebra, you're going to find that because the whole matrix was Lorentzian for all the distances, if you restrict to only the leaves, that matrix is also Lorentzian. Okay, so the eigenvalues are still plus, minus, 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 minus. Okay. So these leaf distance matrices are also Lorentzian. And here is our first theorem. And maybe I'll say it like this. This BT is the Lorentzian matrix I just showed you. So the eigenvalues were plus, minus, minus, minus. If I change the sign of the matrix and I put minus BT, then the signs flip. So it becomes minus, plus, plus, plus. And you might ask, okay, if there's only one negative eigenvalue, how can I push it to make it positive? And so what I'm going to ask is, okay, this thing has a negative eigenvalue. How do I add something to it to make it a little bit more positive? And what I'm going to add is a multiple of the all ones matrix. And so we're just wondering, like, okay, I have this matrix that has one negative eigenvalue. How much, like, what multiple of the all ones matrix do I need to add so that I know for sure it's going to become like all positive eigenvalues, what's called a positive semi-definite matrix. And we found that the constant is 1 minus 1 over n. So we found that if you use 1 minus 1 over n, for sure that thing is going to become a positive semi-definite, and no smaller number is going to work. So that's like the exact number. That's one of our main theorems. I like it. It's also a little bit random to me. It's like, okay, that's nice, but like, why do you care? And I hope to explain to you why we care. But please remember this number 1 minus 1 over n. And I think that is the end of the first part of the talk. Oh, okay. No, there is something that I forgot to say, which is that this result is true for what are called equidistant metric trees. I was sharing with those people that were sitting with me at dinner that somehow, for a very strange reason, I ended up writing some papers on phylogenetics. That's because mathematics has no boundaries. And I wrote a paper on mathematics, and I found that the space that we were considering, which I'm going to talk about later, was the space of phylogenetic trees, space of evolutionary trees. And here I'm thinking of an evolutionary tree where like this is like the origin of life. And then as time goes on, it starts branching. But the distance from the origin of life to today is the same no matter which road I take. So that's what's called an equidistant tree or an ultrametric or a phylogenetic tree. And for some reason, those were the trees that we cared about here. And I'll explain why. But so this is a theorem about phylogenetic trees. So, and I guess I'll say that this is a linear algebra theorem. It's our proof is a combination of linear algebra analysis and combinatorics. So why did we get here? Like, why did we get here? Our motivation was very different. So I told you that I was starting very much backwards. I'll tell you our real motivation, which was matroid inequalities. But before I tell you about matroid inequalities, I need to tell you about matroids. There's something called a matroid. If you're feeling a little tired and not really trying to gather into a new abstract definition, you can think a matroid is a graph, and that's going to be good enough for the rest of the talk. Or if you prefer linear algebra, you can think a matroid is a bunch of vectors. That's going to be good enough for the rest of the talk. If you have a little bit more energy, then I'll tell you that a matroid is an abstract object that is supposed to explain why there are so many similarities between graph theory and linear algebra. There's a definition. I'm not even going to try to talk about it carefully. If you want to read it, you can read it. But matroids are supposed to capture the idea of independence. So in linear algebra, we have linear independence. And in networks, you have like the independence of networks. Like a cycle is superfluous. If you're trying to connect, you don't need a whole cycle because you can just go one way or another. So, and matroids are supposed to model independence. And initially, they were a common framework for graph theory and for linear algebra. But then a bunch of other things snuck in. So it turns out that Galois theory, if you learn about algebraic independence, that also makes a matroid. So a graph makes a matroid, a bunch of vectors make a matroid, a Galois extension makes a matroid, a matching problem makes a matroid, a network routing problem makes a matroid. Matroids are really just appearing all over the place. Okay. What is the matroid in this case? It's the independence sets, whatever independence means in that context. So here, for example, I have listed, here I have a collection of vectors in three-dimensional space. And these are the independent sets. I'm dropping the brackets so that it's a little easier to see. So, for example, B and D are linearly independent. They point in different directions. But D and E, they're parallel, so they're linearly dependent. So that's why you don't see D and E in this list. So these are all the linearly independent sets. I listed them. And in particular, the biggest ones are the bases. What are the triples of vectors that form a basis of R3? These are your options. In a graph, the analogous thing are the cycle-free subsets. So what are the sets of edges that don't form cycles? For example, B and C is listed because if I only look at B and C, they don't make a cycle. But D and E do make a cycle, so I shouldn't list it here. And that was the same. And here you can begin to see the parallels. D and E form a cycle, and that's called parallel elements. But that's literally the same thing as D and E being parallel vectors. And so matroid theory has a notion of parallel and it generalizes both. Okay. But so I chose my examples carefully so that whether you like thinking about graphs, vectors, or more generally, this is going to be our example matroid for the rest of the talk. Okay. And this is what's called a matroid, is this collection. So there are something called the Mason conjectures. Let me tell you the easiest version of the conjectures which is that if you look here on the top right, I'm going to count how many independent sets have size 0. There's 1. How many independent sets have size 1? There's 5 of them. Then there's 9 that have size 2, and there's 5 that have size 3. So you're just looking at what is the number of independent sets of each size. Okay. Here's a conjecture. Those numbers 1, 5, 9, 5 go up and then down. This was a conjecture of Mason in the early 70s. Sounds fairly easy to state, at least. These numbers go up and then down. It took over 40 years for this to be proved. That was like the easiest of these conjectures. The next one is that the black inequality holds. Ik squared is greater than or equal to ik minus 1, ik plus 1. So this is saying that each number in the list squared is bigger than the one to its left times the ones to its right. That's called law concavity. 5 squared is bigger than 1 times 9. That was the weak Mason conjecture. But then Mason got more and more ambitious. And then he said, maybe that's also true if I put a 1 plus 1 over k. And maybe it's even true if I put a 1 plus 1 over n minus k also. Okay. And so he said he had 3 conjectures. The gray one is the easiest one. And with each new factor, it gets harder, right? Because I'm multiplying by something bigger than 1. Okay. And so here you can see what the inequalities say. The first one says 5 squared is bigger than 1 times 9. 25 is bigger than 9. But then the second version says I can also multiply the right-hand side by 2, and it's still true. That's still true. And because that's 1 plus 1 over k. And then the next one is 1 plus 1 over n minus k. I can multiply by 5/4. And finally it says 25 is bigger than 22.5. So that's when it's like, oof, we're getting close. Like, don't stop multiplying by things, you know? He conjectured this, and I wish I could talk to Mason. Like, what were you thinking? But these conjectures, we have loved them for many years in combinatorics because they're very easy to state. I just stated them to you. But as I often like to say, these law concavity statements, if you're trying to prove them, like if you have a new sequence and you see, oh, it goes up and then down, maybe that's true. Maybe it's usually either you try to prove it and you prove it that afternoon, or if you didn't succeed that afternoon, you're probably gonna have to wait decades. That's the history of this field. Either it's like some kind of algebraic manipulation that you can figure out, or it's probably something really deep that you're gonna have to do something very deep to understand. And you might have heard the story of my friend, co-author, collaborator in this paper, Juni Ha, who started as a poet, became a mathematician, just won the Fields Medal, which is the highest honor in mathematics, a couple of years ago. And one of the main reasons that he won that award is that he was able to prove with his collaborators these conjectures. And again, it's a little bit random. Like, why do you care that these numbers go up and down? I mean, I care. Like, it's nice, you know. Do you want to spend like years and years and years of your life doing it? Maybe. But the reason that we in combinatorics are so excited about these things is that, so this is in my mind one of the most celebrated papers in my field in my life. Adiprasito, Ha, and Katz managed to prove Mason's conjecture and Rota's conjecture, which, you know, again, the theorem is this strange inequality. But what is interesting about it is that they really had to understand something new about graphs, vectors, and matroids, and they had to invent something called the tropical Hodge theory of matroids. And maybe I'll just say one word, which is that matroids they seem very combinatorial. I had this paper with my colleague Carly Clivens where we said, oh, matroids actually have this geometric model, something called tropical geometry. And there's a pretty deep branch of algebraic geometry called Hodge theory. And Juni told me like 10 years ago, maybe these tropical things satisfy Hodge theory. And we were all like, that can't be. Like, why would that be? There's no evidence. But he's a mathematical optimist, and he decided to try to prove that these objects that are not algebraic geometry actually behave like they are algebraic geometry, and then invented this whole theory. And the consequence is the inequality, but really what's interesting is that it just started a whole new field of mathematics. But he still was itching like, oh, but what about the extra factors? He couldn't prove the extra factors. And eventually they were able to prove the hardest version of the conjecture. And they had to invent a whole other theory, which is the theory of Lorentzian polynomials, which is now, instead of relying in algebraic geometry, this is the same word Lorentzian from the beginning. This is an analysis thing. It's like about analysis and linear algebra and science of eigenvalues. And in this, when you don't get the paper published in Annals if you don't have like a really radically new idea. These two papers really contain two of the most interesting ideas in combinatorics of recent time, and they were trying to prove these conjectures. So that's why we like these conjectures so much. Okay. Okay. So and if you're curious to know more about this, so he won the Fields Medal, and in the citation, a lot of the details are explained of how he did this, and the tropical geometry involved, and the matrix theory involved. And the thing when you work with somebody like, I'm not the kind of mathematician who says, let me try to solve a 50-year-old problem that nobody has been able. I don't know. It's not something that I kind of. It's not how I have carried out my mathematical life. But you know, June used my work in this, and one day he just called me and said, "Hey, Federico, there's this other conjecture that I think we can do it," and that's how I got involved in this, and that's how I started collaborating with this team of people. And what I want to tell you about is this happened last year, that we said, you know, maybe we can solve another version of these conjectures, which is the polynomial Mason conjecture. Okay, and it says the following. Let me say the gray version. Okay. So remember that, I mean, this is the same list as before, and remember that each number squared was bigger than the one to the left times the ones to the right. Okay. I'm doing the same thing, but instead of counting, I'm actually listing the sets. So you see this ABC plus ABD plus ABE. That's the third list. That's the list of length 3. And so what I'm doing is I'm taking like all the independent sets, and I'm squaring that, and I'm saying that's going to be bigger than the ones of size 3 times the ones of size 1. Okay? But these are no longer numbers. These are going to be polynomials. And so what we're saying is that actually this polynomial is bigger than this polynomial. And what does it mean to be bigger? It means like all the coefficients are bigger. And just to point out, here's a warning sign. A squared plus B squared is bigger than 2AB, or numbers, but not as polynomials. See what I mean? Because the coefficient of AB here is 2, the coefficient of AB here is 0. What I mean is that every single coefficient should be bigger. So it's not just that the numbers are equal, but that the polynomials are, not just that the numbers are comparable, but that the polynomials are comparable. Igor Pak asked this question, and he actually thought the answer was no. But we proved the answer is yes. So not only are the numbers satisfying this inequality, but as polynomials, they satisfy this inequality. And then Igor said, okay, the first one might or might not be true, but I could also make it harder by putting this blue factor that I had before, and that makes it even less likely to be true. But we also proved that that's true. And then he also tried to put the pink factor, but he realized that with the pink factor is not true. So that it's very easy to find a counterexample to that one. And so then he asked, could it be true that these are just polynomials? And our main theorem is that that's true, okay? And similarly to before, our first proof of the gray one, it's a theorem that we liked, but we liked the method more. And the method is that we had to develop a theory of Lagrangian geometry of matroids. And I didn't know any Lagrangian geometry before this, but we somehow saw shadows of connections between matroids and this field called Lagrangian geometry, and learned enough to find the right tools. And then in order to get the extra factor, we relied on the theory of Lorentzian polynomials. Okay. So that's our first inequality that we were able to show. Okay. Let me try to make this very concrete so that you understand this phenomenon very clearly. Same polynomial as before. Okay. And I'm saying that the top polynomial is bigger than the bottom polynomial, coefficient by coefficient. So let me pick a coefficient like A, B, C, D. So A, B, C, D. So how can I make an A, B, C, D here from the bottom product? I can make an A, B, C, D in the bottom product, for example, by choosing A, B, C here and D here. Okay? But then I want you to look at this picture. Green is A, B, C, and purple is D. And so what I'm saying is I can take A, B, C, D and put it into a green independent set of size 3 and a purple independent set of size 1. And there's 3 ways of doing that. There's 3 ways of taking my set of size 4 and splitting it into one of size 3 that's independent, one of size 1 that's independent. And that should be less than the ways of doing it with 2 and 2. And those are the ways of doing it with 2 and 2. And not only should this number be bigger than this one, but it should be bigger than that one with that extra blue factor. Okay? And so this statement is saying something about taking any set and breaking it up into independent sets. Okay? In the context of graph theory, this is like, how can you take some graph and split it up into 2 trees of various sizes? And the theorem says that if you want to split it up into I and L sizes or into J and K sizes, it's going to be easier to split it into sizes that are closer to each other, like 2 and 2, than sizes that are farther to each other than 3 and 1. That's what the theorem says. It's a very concrete theorem. Something about independent partitions. Okay, so that's our first theorem, our first like matroid theorem. Now, the other theorem is another generalization to something called valuated Mason, and that involves something called valuated matroids. And again, I don't think that I want to really say what a valuated matroid is exactly, but I want to say that it's something richer than a matroid. So how can I explain this? One way that I can say this is that if you had a bunch of vectors and you want to say, okay, are these 3 vectors a basis? One way of seeing if three vectors are independent is by taking their determinant. So 3 vectors are linearly independent if their determinant is not 0. So the determinant knows, is it independent or is it dependent? But now you could say, okay, if they're independent, can I measure their independence quantitatively somehow? And so, for example, I could say, okay, if that number is not 0, that determinant is not 0, how even is it? Like, what's the power of 2 that divides it, for example? And so I'm going to say, okay, if I have a basis, I want to say, is it like a little bit even? Is it very even? So if the determinant is 2 or 6 or 22, then I'm going to call it not very even. It's only divisible by 2. But if it's 32, then it's like, oh, that's very even. That's divisible by 5. So that's how you measure the basis. So it's some way of it's like a quantifying of the matrix. And if these words are familiar to you, like matrix subdivisions or tropical Grassmannians, that's where this comes from. I can talk to you about that after if you would like. Okay. But that's a evaluated matroid. And there was a conjecture by Jen Siracusa, Rincon, Schleiss, and Ulrich. There's a theorem which is that, okay, now they say take the independent sets, and for each independent set, instead of counting it for 1, you're going to see, how divisible by 2 is it? So if it's divisible by 2 ones, I'm going to put a q to the 1. But if it's divisible by 2 to the 5, I'm going to put a q to the 5 here. Okay, so it's like a quantitative refinement that for each basis or each independent set, you're going to weigh it by how independent is it. Okay, and q is some parameter between 0 and 1. In mathematics, we like to call this like quantization. And what they were able to prove is that Mason's inequality was true not only for q equals 1. If q equals 1, this is just the number of independents. But they were able to show that this is also true as polynomials in q. And they were also able to show that that's true with a blue factor. And they were not able to show, but they believed that it was also with the pink factor. And this is our other theorem, is that this is also true, okay? Using the theory of Lorentzian polynomials. One brief thing that I'll say at this point is that, do you remember that extra factor we had for the tree matrices? 1 minus 1 over n? That's exactly where that factor comes from. That pink 1 plus 1 over something it's literally the same thing that I started in the first. So the reason that we were interested in that precise number 1 minus 1 over n is that that's the number that gives you this factor. So let me say just a little bit about this. I want to give you an indication of what this theory of Lorentzian polynomials is in a very brief manner. And by the way, I talked to several of the students, and I noticed you all doing the same thing that our students do at SF State, that you're like, oh, I'm more of an algebra kind of student, or oh, I'm more of an analysis kind of student. Sorry, it's not that way. It doesn't work that way. So we're gonna do some analysis now. Point being, like, these mathematical fields are not disconnected in that way. I'm going to talk about when polynomials are Lorentzian. Okay. First, I'm going to do it for quadratic polynomials, and these are polynomials in many variables. Okay. So a very big polynomial in many variables is strictly Lorentzian if and only if the Hessian is Lorentzian. Okay, I don't remember what Hessian is, but I can look it up. So if you have a polynomial, this actually comes up when you're doing like multivariable calculus, which I learned at some point in my life. And it says, okay, you're supposed to take your function and then take all the possible double derivatives. So I take my function and I make a matrix where the ij entry is the derivative with respect to variables I and j. I get some matrix, and I'm going to look at the eigenvalues of that matrix and see if they're plus, minus, 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 minus. And if that's the case, then that gets to be called Lorentzian. Okay. That's if it has degree 2. If it has degree 3, what I have to do is take the derivative with respect to x1, which is quadratic with x2, and so on. and I get a bunch of quadratic things, and all of them should be Lorentzian. And if I have a polynomial of degree n, and I want to know if it's Lorentzian, I have to take every single derivative that brings it down to degree 2, and I'm going to get an ocean of matrices. Each one of these matrices should be Lorentzian. If that's the case, that's going to be called a Lorentzian polynomial. Okay. I'm oversimplifying a little bit, but this is essentially the case, and the point is you're looking at eigenvalues of derivatives of your function, okay, and checking their sign. Why is this relevant? Because if you have a polynomial in 2 variables, here's a theorem, a polynomial in 2 variables with positive coefficients is Lorentzian, strictly Lorentzian, if and only if this inequality holds, which ends up being exactly the strongest version of Mason's inequality. Okay? So if you want to prove something like this, that means you should prove that some polynomial is strictly Lorentzian. But this thing has degree n. It's easy for things of degree 2 to be Lorentzian, but you need something of degree n to be Lorentzian. And so if you want to prove that something of degree n is Lorentzian, you actually have to come up with a whole family of things that are Lorentzian and they're close under derivatives, and you can't just discover one of these creatures, you have to show that they belong to a very large Lorentzian family. How do you do that? You need to find Lorentzian things in the world. So where do you look for Lorentzian polynomials? I mean, this is a very, at least for me, when I first read this was really intimidating, and I would have no idea where to begin looking for a Lorentzian polynomial. But here's another theorem. The support of a Lorentzian polynomial, meaning like the places where the coefficients are non-zero, are exactly polymatroids. And okay, I happen to know what polymatroids are. So if I need to look for Lorentzian polynomials, then what I'm going to do is look at what are all the polymatroids that I know, try to build polynomials out of them. And because these conjectures come from matroid theory, maybe it's reason to be optimistic that, okay, we started with matroids, so maybe there's some Lorentzian phenomenon going around. Okay? And our main theorem is that that's the case. And so what we show is that for any evaluated matroid, if you look at this thing, it's just what we needed for this architecture to be true. So we care about this very specific polynomial, but we actually have to come up with a big family of polynomials. And what we find is that this particular expression is Lorentzian. That's our main Lorentzian theorem. Okay? And I won't get too much into the details except to show you, okay, it looks like that. In order to prove that we have to take all the derivatives, do it. And the corollary is the polynomial Mason and evaluated Mason. So the way that we show these two conjectures is that they actually follow from that Lorentzian. Okay. And maybe the one thing that I'll say about this theorem, let me sketch a proof. And again, you're not meant to understand the details, but just to give you an idea of what this works. We're trying to prove that these things are Lorentzian. So you have to check all the derivatives. And so you have to take this thing and take every possible derivative until you get to degree 2. And so we did that. We took all the derivatives until we got to degree 2. And believe it or not, when we got to degree 2, what we found was the matrices from slide 1. And so that's why we cared about those matrices. Those matrices that seem kind of random. It's just we're trying to make this architecture to work, and then we put it all to work, and then like take derivatives. And what we found is that we needed to prove that this was a positive semi-definite matrix. This is like the quadratic floor of the Lorentzian tower, and then up there is the Lorentzian thing that we cared about. And as I said a moment ago, that's why that factor is important. It's exactly the factor that we needed. Okay. Last thing I'll say is that whatever evaluated matroids are, the ones of rank 2 are exactly phylogenetic trees. And I feel very lucky that I happen to have some papers about phylogenetic trees that gave us the tools to do some of these things. And so it's interesting because actually Buneman was a biologist. And so we're actually using a biology theorem in this proof. That's the next to last thing that I wanted to say. And the last thing I'm going to say is that Chris Ure and Jun Ha asked a more general question, which is, okay, that's true for matroids, but they ask, for which functions is this thing Lorentzian? It's true for matroids, but can you say what are all the functions? Okay. And we found the answer is that it's precisely for something that is called an M-natural concave function. Okay. I'm not going to tell you what that is, except to say that these are objects that people have studied in optimization. And so we were interested in when weights are Lorentzian. And it turns out that this had been studied in optimization. And Murota had actually showed that these things called M-sharp concave functions were the same thing that economists call the gross substitutes property. And so we have a theorem that I do not at all understand, that some polynomial is Lorentzian if and only if there is an economic situation where my summary of what this means is there's some way of assigning prices to things in the world so that sharing is good and trading is good. And that made me feel a little bit better about the world somehow. But anyway, that's a good place to stop. Thank you so much for your attention.
Questions for Federico? Luis up there.
Oh, by the way, Federico has a rule, which is that students have to ask the first question, and every time that a student asks a question, they unlock a question for the faculty. So we got started well.
So my question is like, can you give some insights, maybe like intuition on what those kind of like constants maybe like represent when you talk about those inequalities? Like they kind of like make it the bound more strict, right? And what can those kind of like constant represent?
Okay, so maybe I'll go back to this slide because I find those. I used to find these constants kind of annoying, and to be very honest with you, I was just like, why should I care about these extra constants? Like that's kind of like feels very like. I don't like this formulation, but I like putting it in this way because it has this kind of color coding thing that helps me tell you what are the 3 steps. But I like this formulation better, which is to say that not only are the AKs log concave, but they're also log concave when you divide them by this. And by the way, you might be aware, at least when I started in this, the only log concave sequence that I knew was n choose k. So Pascal's triangle goes up and then down in each row. And it's also true that in Pascal's triangle, if you've never proved it, I invite you to prove it. In Pascal's triangle, each number squared is bigger than the 1 to the left times the 1 to the right. And so this is saying that this sequence is log concave, even if you divide it by that log concave sequence. But I think that's the best explanation that I have. It's just like a more restrictive.
Other questions?
I'll unlock another question for the faculty. I'm not a mathematician, I'm a physicist, but I'm really curious about the practical, maybe even societal applications of these theorems, maybe just more on the application side. Thank you.
Thank you for the question, and I'll tell you what has been my experience as a mathematician, which is that as I think, I don't know how much you can tell that my training has been pretty pure, but the more, I mean, I have many papers where it looks like a pure paper, and all of a sudden, it's like, what is phylogenetics doing here? What is this? By the way, if there are any economist majors here who can tell me anything about the gross substitutes property, I really want somebody to explain to me what that means to you all. And this is actually like an open problem. Like okay, we have this whole theory of Lorentzian polynomials that mathematicians are so proud of, that in this case is exactly equivalent to gross substitutes property. So can we say something cool for the economists that they don't know? And this is the kind of thing that happens. Murota is one of the experts in something called discrete convex optimization. And he's really coming from optimization. And optimization, I mean, matrix theory also, like, what's an independent set? Let's say that you have a country and you have a system of roads. One way that I like to tell this story is like you have a bunch of roads. Imagine there's some hurricane that wipes out all your roads, and now you're going to rebuild roads. But your country just had a big disaster. You're trying to do it in the cheapest way, and so you're trying to connect in the minimal way possible. Okay? And so a tree is a way of connecting the whole country without building any extraneous roads. And you might ask, okay, out of all the ways of building roads in a country, what's the cheapest one? It's a very important question. And this is something called the minimum spanning tree problem. And this is one of the births of Matroid theory, that Matroids exactly tell you how to solve that problem. So I know it doesn't seem like it, but there's a lot of applications here, and I think sometimes there's a big gap in communication, because in a lot of my papers I'm like using theorems from algebraic geometry and using theorems from optimization and finding that these communities have just never talked to each other. So I just don't believe there's that line. But I think your question is still really good. Like, okay, that's a nice theory, but like, how do we actually apply this? I would love to know. And in this particular project, we don't know that yet, but like I said, some of these theorems are like a month old, so yeah.
Other questions? Jaden.
Could you say something about what a polymatroid is? And also, I had another question, which was, you wanted to show that a certain matrix was semi-definite, positive semi-definite. Why did positive semi-definite suffice and not like Lorentzian?
Okay. So let me. Yeah, why positive semi-definite? So has anybody heard of a Schur complement? Okay. This is some, like, for me, deep linear algebra that I had never used. We're actually trying to prove that a matrix is Lorentzian, meaning it has one eigenvalue of positive and the other is negative. And the way that we did that is that we took the Schur complement. Okay, so we kind of knew what happened with the positive eigenvalue, and we needed to prove that the other ones were negative. And then there's just some technical trick, which is the Schur complement should be positive definite. So our original matrix being Lorentzian ended up reducing to this one being positive definite, and actually it's in that Schur complement step that this factor came up. So the answer to that question is a little bit technical. It's just that wasn't our choice, is what the proof asked for. Sorry, remind me what the first question was? What's a polymatroid? What's a good way to explain this? I have to stop myself because I could talk about this for many hours, but I think maybe the best thing that I can say about that is that just like matroids model sets of vectors, polymatroids model sets of subspaces. So if you have only like this vector, this vector, this vector, that gives you a matroid. But if you say this line, this plane, this four-dimensional plane, then that gives you polymatroid. So it's something more general, but still very closely related.
Or geometrically generalized permutahedra for those.
Oh yeah, so some of you have heard of generalized permutahedra. Same thing. A polymatroid is a generalized permutahedra. So if that means something to you, great.
Any other questions? Profs, you've been allowed or unlocked 3 questions.
Right behind you, Andres, also.
So you've proved like the hardest version of these inequalities. Is equality ever attained? And if not, is anyone trying to make the problem harder?
Thank you for that great question. And okay, here I'm going to admit that sometimes in the process of writing a paper, your co-authors know things that you don't know. So if Sergio was here, Sergio could tell you the answer to that, because there's something that we wondered is, when does equality hold? It turns out to be pretty subtle. And there is a section of the paper that I haven't read yet that Sergio wrote, and I'm here, so I haven't had a chance to read it, but he worked it out. So in the paper that'll be there, but I couldn't tell you exactly what the answer is. Equality does hold, yeah. And I mean, so the question was like, for which trees does equality hold? So I have the vague memory that he told me that it's for claw trees, where it's just a node and it's like a flower. I think he proved that that's the only time that equality holds.
So I actually have 2 questions. My first question is that, can you provide an intuitive explanation about tropical Hodge theory? I'm just curious about it.
Well, what an easy question you're asking me. Oh, wow. I like this challenge. Let me try to say something about Hodge theory before we go tropical. And I want to preface by saying this is not my field of expertise, and this is a field where, like, if I really have a question, I ask June and Graham, and like collaborations, there's always people that know better something, and there's some other places where they would ask me questions. This is a place where they would ask them the question. But one thing that I'll say is that when you have a nice smooth variety, it could be a parabola, it could be a hyperboloid, there's something called the Chow ring. And the Chow ring basically tells you, inside of your geometric object, inside of your variety, how do the sub-objects intersect? Okay. So I don't know, if you have like a paraboloid like this, then you could take a parabola like this and a parabola like this, and then they intersect at this point. And the Chow ring knows that. And this Chow ring is, as you can imagine, a very complicated ring, because it's supposed to know how every subvariety intersects with every other subvariety. But this Chow ring ends up being like very, very beautiful, and has a lot of structure. If words like Poincare duality mean something to you, like this thing is graded, and the size in dimension 3 is equal to the size in dimension -3, and there's actually a hard-Lefschetz theorem about how you can get from the level 3 to level n-3, and there's a bilinear form that ends up being I forget if Lorentzian or positive semi-definite, but there's a bilinear form that has these kinds of properties. And so basically the point is that algebraic varieties have a lot of structure in how their subvarieties intersect. And there's much more to this, and this is like a rough idea of Hodge theory. The simplest thing that I can say about this idea of combinatorial Hodge theory is that June kind of wondered, what if matroids also had that property? What if matroids behaved like smooth projective algebraic geometry? And there are reasons why they shouldn't, because they're not even algebraic geometry. But we had some evidence for, like, oh, this is giving like Hodge theory vibes, and so maybe and it turned out that we actually had to. Algebraic geometry was not enough to prove this, because this is not algebraic geometry. So we actually had to find like combinatorial versions of all of these statements. Then we have to define a combinatorial ring. We have to show how to subdivide it, how to prove theorems like this. And that's the program of combinatorial Hodge theory, is to do like a combinatorial or a tropical version of the structure that is known in algebraic geometry. that's my best. That's my best 2 to 5 minute definition of what this is.
I think maybe this is a good place to stop. So before well, let's end here, but before you all leave, let's thank Federico one more time. Thank you once again for joining us. We hope that we'll see you next year for the next Moody lecture. Have a good night, y'all.